All right, welcome back to the fourth episode of our series on writing a Lisp with Claude. If I fixed a bug since last time, if you remember, we added support for quote, and I mistakenly thought that quote was not a valid symbol character, but it actually is. So if I go and we got a closure REPL up here, I can say a prime and set it to 5. So a prime is a valid symbol. So I fixed that bug in our implementation, and now you could put quotes in your symbols. All right, for this episode, I had originally said that we were going to add support for raise, but I want to make this a little more fun. And we're going to add some support for some built-in functions right now. I'm going to start with operator functions, your math operators, plus, minus, divide, and multiplication. And so for that to work, I'm going to we have an environment, but it doesn't have a parent. I want to have a parent environment, and that comes in later when we have scopes. But for now, right now we have a global environment, but I want to put all the built-in functions in an environment that is above global. So it's kind of a built-in environment. Think of it as the language core environment, Swish core, where we're going to store our built-in functions. So let's try this. So let's start with the environment. Update our environment class so that it has a parent environment. And when you look up a symbol in the environment and it can't find it, it will look in the parent environment. All right, that's all we got to do right now. I think we're going to start with that. Let's go to plan mode and go. This shouldn't take too long. Of course, we're starting a new session, so it's got to read all the docs again and all the code and get familiar with things. You'll also notice that we're using Sonnet 4.6. Before we were using Opus, and they came out with a new model. Sonnet 4.6 is supposed to be as good as Opus 4.5, so I figured we'd go with it. Let's try it. All right, so it's saying, do you want to proceed? And yes, don't ask again for grep. It's taking its time. Okay, it's got a clear picture. Yes, the change should be small. And we got a plan. Let's take a look. All right, the environment class has a flat single level namespace. The environment needs a parent. So, okay, yes, that's what we want. So now we're going to add, that's what it currently looks like. It's going to add a parent. In it with parent. Get will look, okay, yeah, that looks good. And it wrote some tests, so let's go. Pretty simple changes. It's going to add some tests. You'll see that we've updated our eval file, and our evaluator tests. Okay, it says it's done. Let's go verify the test ran. And it did. Right now we really don't have a way to test that in our REPL, but we'll get there during the session. So let's see what it did. In eval, it's got, it added the bindings, or it added the parent lookup, and in the evaluator tests, it added some tests for looking at the parent. Okay, that looks good. Let's go on to the next step. First of all, I'm going to say commit this. Yes. All right, so now let's move on to the next thing. Now, in our interpreter, we need a parent environment of our global environment, which is where we're going to put in all the built-ins, all the Swish core. So let's see, in our interpreter, in Swish kit.swift, add a parent environment to the global environment. This parent environment will be where we define core language symbols, functions, etc. Also add this to our Claude.md. Okay. Let's go from there. Let's go that. Just do that. All right, it's ready to write a plan. Taking a time. Okay, here we go. Core environment, built-in symbols, functions, read only by convention. Parent, global environment. Okay, yeah. Separates this how this mirrors how Clojure separates Clojure core from the user namespace. That is correct. So we're going to just update the eval class, add a core environment property, and make environment's parent point to it. In our evaluator. Okay. Environment's going to no longer use a let inline initialize. Okay. Claude.md, we're going to add this to the Claude.md. About a core environment. All right. Gonna write some tests. Let's do it. Okay, it's updated the evaluator. It's updated Claude. It's updated the tests. All right. Run our test again. We can run the REPL. Shouldn't change anything. But if I do an A, it's there. If I do a B, it's there. Seems to work. All right. Now, let's verify the code. And we've got a core environment now. And we've got some tests, more tests that just test the parent environment. And our Claude.md now has a some verbiage about having a core environment. That looks good to me. Let's commit this. All right, now that we have a core environment, we can define some functions. But before that, we need a way to represent a function in our ASTR, an expression class. So add a case for our expr that represents our AST for a function. A function has an optional name because eventually we will have closures or anonymous functions, so they won't have a name. So it has an optional name, an array of arguments, which should just be symbols, and a body, which is another expression. Let's plan this. We forgot to say anything about printing, but I'm not going to worry about that right now. We can add that later. All right, it's going to write the plan out. Okay, here's our plan. The expr asks to support first-class functions. Lambdas named a function cases needed. It carries an optional name, a parameter list, and a body of expression. This is a prerequisite for implementing fn and function calls in the emulator. You'll notice that it's filling in things that I didn't really specify because it knows basically how closure is implemented. It's been trained on that. So in the parser.swift, add an indirect function clause. So indirects, because exprs can also contain expr, so it's recursive. So we need that. Function name, optional name, parameters, and the body. Yes, that's good. It's going to be equatable. Good. Because we need to compare expressions. Oh, it's going to go ahead and add print for me. And I think that works for now. All right, it's going to add some evaluator tests, printer tests, equality tests. All right, that sounds good. Let's do it. You see it's modified a bunch of stuff over here. All right, it's done. Let's run our tests again. Maybe I don't need to do this since Claude's already doing it, but habit. Not quite trusting of these things yet. Let's see what it did in our REPL. It updated things to print out functions. And in our parser, I'm surprised it did something. Oh, I just added the case for our function in AST. Okay. And in the printer, well, let's look at the evaluator first. It added function is going to evaluate to itself right now. And in the printer, added a case to print out the functions, a function. And we added some printer tests. More printer tests. Okay. All right, that looks good to me. We can't really test anything in the REPL on that because we can't define functions. But that is where the next case comes in. So let's commit this. All right, so now we're going to add our first built-in function, and let's start with the most simplest case, the plus operator. So the plus in Lisp, there aren't really operators, there's just functions. So plus is just another function, and it works on all numbers. So we have decimals, we have ratios, we have integers, and so it all should work on that. And also in Lisp or Clojure, you can add a whole bunch of numbers at once. So it can have multiple arguments. Yeah, even if you give it no arguments, it returns 0, as you can see. And one argument, it returns the argument. Okay. So here we go. Add a built-in function to the core environment named plus actually I need to back up here. We have functions, but we need a special case of like a native function. So let me ask, I think I know how to do this, but I'm going to ask Claude how to do this. We need a way to register native functions, which can also be used to register built-in functions. What do you suggest for this? I think we need a new case for our expr enum that represents a native function. It would have a name and arguments, and then a Swift closure to actually implement a function. We also need to be able to specify if a function can accept a fixed number of arguments, zero, including 0, or a variable number of arguments. All right, let's see what it has to say about that. This is an important thing to note. Closures aren't equatable, so then that would break our equatable implementation. So we may have to do something about that. What does it say? What did it say? He needs to address that constraint. Yeah. We need a custom equal implementation. Exactly. All right. So to implement built-in functions, we need a way to register Swift closures as callable Swish values. This requires an arity type to express fixed. Yeah. a registration API, an evaluator. It's doing a whole bunch of stuff. Function call dispatch in the evaluator, and a custom equatable implementation. Okay, so there it is. It's got an arity. This is very similar to what I did when I did this by hand. So you got a fixed number of arguments, or you got a variadic. We got a native function case that accepts a closure, which takes an array of arguments and returns an expression. It's going to do the equatable on the EXPR. Add it, remove equatable. Okay, yeah. Add a arity mismatch error. Okay, yeah. Add a native function to the self-evaluating arm in the list evaluation branch before the fall through elements map valid resolve the head, and if it is native function validate arity, evaluate arguments, call the closure, and add a register method to the evaluator. Okay. Core environment. Sources added then. Okay. Added thing. I'm gonna actually modify here because I want registration should happen in the interpreter Swish class. Let's verify. Is that a class? It is a struct. In the Swift struct. That's not quite right. That'll be for user registration, but for registering in the core functions in the thing, I think the evaluator for now, let's accept that. If we have to change that later or add another registration facility, we can. So let's just add auto accept these edits. All right, so it actually filled in a lot of gaps that I didn't specify. So let's see how good a job it does. It's modified the evaluator, it's modified the parser. Just for the EXPR, I don't remember. I'm already losing my ability to remember code because I didn't write it. All right, it's already added. Changed the code, it's doing tests. All right, let's run the test again. 453 tests. We had a bunch of warnings up there at the top. All right, we're starting to get into Swift concurrency issues. I'm going to have to resolve that at some point. Okay, those are just notices about starting the test, but otherwise the test passed. So let's, I'm not going to run the REPL just yet because I'm not sure what it did. Let's go look at what it did. All right. In the interpreter, it added some stuff for the native function. In the parser, we added arity and our native function. And an extension for our equality custom implementation. And the printer, let's look at the evaluator first. We've got an arity mismatch error. We've got that warning, which we're going to have to figure out. An arity mismatch printing out. And here's our evaluator. Native function and function is going to self-evaluate, but when we have a list, and we're going to look if the first value of the function is not a special form, but it's something else. If the head is a native function, then we're going to call the body of it. It should actually do the same thing for functions, but we don't have that yet, so I won't worry about it yet. The printer will print that out, and we've got a bunch of evaluator tests that it added. All right, let's try this out. Let's run it. All right, so we know we have a plus. If I type in plus, it says undefined. It should actually print. Oh, see, it's not working. I didn't see anywhere where it registered the plus function, so maybe it hasn't done that yet. I thought it said it had done that, would do that. So let's see. Oh, I just did it in the tests. So I'm going to commit this for now. And now I'm going to say add a built-in plus function and register it in the core environment. It will be a native function and take a variable number of arguments. If given no arguments, it should return 0. If given 1 argument, it should return the argument. If given more than 1, it should add up the arguments. It should also work on integers, floats, or ratios. I'm wondering if I need to tell it how to add ratios or if it can figure it out. I'm going to see if it can figure it out. So let's just do this and see what it does. You can do ls whenever you want, but it's writing our plan. All right, so we can now implement out the plus function as the first, variadic, numeric, with closure style type promotion, and lives in the core environment. Okay, all integers, any float present will become a float. Ratios, okay, any ratio present, no floats becomes a ratio, and it ends convert to ratio. Results reduced. Okay, yeah, that's exactly what it's supposed to do. New error case for invalid arguments. Register core functions. Okay, yeah. Helper. Here's our numeric add functions that's actually used in the closure that it registers. Got some tests. Looks good to me. Let's do it. All right, it's updated the evaluator and the tests. Added a new core function for registering our core functions. And some core tests. Oh, it's got some failing tests that's going to have to fix. All right, it's done. Let's run the tests ourselves just to verify. Again, they passed. I'll have to look into those warnings on off air. Let's see what it did. So it's got the core where it's registering core functions. Okay, and there's our numeric add. You'll see that if, okay, looks like I told it, if there's no arguments, it returns 0. If there's 1, it returns the argument. If it's one of these, if it's not, if invalid, we get an invalid error. And then it drops the first argument, which is the actual function name, or the, and then it adds these, adds them up. And here's our add. So if they're both the same type, relatively simple. We promote integers and floats, ratios are handled, and yeah, that looks good. We got some core tests that just testing the plus operator, and in eval we got our new invalid argument error. We've got some more error printing and initializer for registering the core functions. All right, that's the big test. Let's take it for a ride. Okay, so all right, let's do plus 1. Actually, it's plus. Give plus 1 gives us a 1. Plus 1, 2, 3, 4, 10. That's right. If we add 1 and 2.0, we get 3.0. If we add 1 and 3/4, we get 7/4. That is correct. 5 seconds. Okay, yeah. 2 doubles. Get a 5. All right, it's looking good. Now if we enter a plus, now we get that native function that we got an error before last time. Let's try invalid arguments. So if I give it a string, it's going to say invalid argument. Okay, let's give it a number and a string. There we go, invalid argument. What else? I think that's it. So I hope that's a little more interesting this week. Next week or next time we will add more built-in functions for the types we have. We especially need a print function so you can run programs that actually do something. All right, until next time, please like this video, subscribe if you like it, tell your friends. I put a link in the show notes for the repo that goes with this, and also there's a link to buy me a coffee if you feel like you want to support my work. I would really appreciate it. I've been unemployed for quite some time, and so it'd be nice to I don't know, get appreciated for my work. So until next time, thank you.